Alright, hey guys, how's it going? I wanted to go over the topic of twice NAT with regards to NSX-T because this is something that, coming into NSX with a Cisco background, I was aware of twice NAT and just could never figure out how to do that with NSX until recently, and come to find out it actually has been possible the entire time I've been using it. It's just it's a bit hidden, and so this is going to be the network diagram that we're working with, and just briefly I want to go over why I think it took me so long to get this figured out. Is because when you go to make a NAT rule in NSX-T and you go to select what type of NAT that you're going to do, if you look in the list here, and so this version of NSX is this 3.0, I believe. Yeah, so version 3.0. If you look in your list of types of NAT that you have SNAT, which is source NAT. You're going to change the source IP address. DNAT, reflexive NAT, which is going to be used when you have multiple uplinks on your Tier 0 gateway. And this is basically the way that you get around stateful forwarding of your edge device, because if you have ECMP, multiple edges connecting to your top of rack switches, of course you can't do stateful you can't have a state table for that packet because you never know which interface is going to ingress or egress from. So that's the purpose of the reflexive NAT rules. You have a no SNAT and a no DSNAT. So usually I'll see these when configuring IPsec tunnels, so you can perform a no NAT. But one of the things you don't see is twice NAT, and it's confusing because with so many other parts of NSX, there's often a corollary in the web UI to what we used to do on the command line. So I'll give an example. If I go to the Tier 0 gateway and go to routing, BGP. Let's do BGP is a better example. So, if you had say a Cisco device, but many other vendors, you pound out some things on the command line. You notice here that this is all, all the things that you used to configure on the command line are now represented in the GUI. And so, it's natural to think that, okay, if there's a feature that I'm familiar with, then that should also be represented in the GUI. And as we looked at in the NAT configuration, there is no twice NAT. All right, and so let's talk a little bit about how you get around this with NSX. Right, it's not there. I'm going to bring up a diagram here. And it took me discovering this packet processing diagram. I actually this was referenced to me by a colleague. It took me a while to actually find it, and I wanted to make, to the degree that I have any voice with NSX or any network engineers, I wanted to make it known, because I don't think people should have to wait 2 years to figure out how to get twice NAT to work. And one of the things you'll notice is that you have for your interfaces, you have inbound packet processing. So this will be an order of processes that takes place on the packet as it ingresses the particular interface. If IPsec is decapsulated first, then if there's any DNAT rules that need to be DNATed, then that'll happen. Destination NAT, firewall rules will be applied. Load balancer functionality happens here. Service insertion, so on and so forth. I'm not going to go through all of these. You guys can look those up if you really want to. My main concern is that destination NAT happens here on the ingress, and then source NAT happens on the egress. And the net effect of this, in order to get twice NAT, and maybe you think about that in air quotes, because you're going to have to configure 2 NAT rules, and you're going to get the net result being the packet will have a new destination IP address and a new source IP address. And let's kind of take a look. This will be your IP header. All right, we'll use red, and we'll shrink that a bit. So, imagine this is an IP header going into a router. To do twice NAT, you'll have 1 NAT rule. You'll strike this out. Maybe we'll have source NAT of 1, 1, 1, 1. We'll strike this out and have it be 2.2.2.2, and then the packet goes on its way. And that would all be accomplished with 1 rule historically. And as see with this diagram that's going to be on the ingress of your interface. We'll undo. Right, your packet goes to ingress, then your destination NAT's going to happen, and you're going to apply the 2.2.2.2, and then as the packet egresses towards its, after it's routed towards its destination, this will be stripped off and it will be replaced with a new IP address. So hopefully that kind of gets the idea of NAT and what we're doing here. And let's cancel this. So let's give an example. I'll go to my diagram, back to this again. So what we're doing, actually not this one, this one. So we're going to set up a NAT rule here. As a matter of fact, a NAT rule is already configured. And that NAT rule basically is saying it's a destination NAT rule. Any packet, well, rather a packet from any source IP address that's a destined for this 192.168.100.50, we're going to destination NAT that to 10.10.120.10. And you'll notice that's correlated with this device here. So this will basically link any packet coming from any source, change your destination IP address so that we can route it down to this location here. And you'll see that works great. Let's change colors here. We'll go purple. That works great for client requests coming from outside in. It gets destination natted and forwarded on to its merry way and then sent back as well. You'll get the client request will be answered, but it will cause a problem if you're coming from another tenant inside the NSX domain. The packet will make it to its destination, but the packet won't be able to come back, and we'll take a look as to why that is, and we'll fix it with TwiceNet. So first, let's just take a look and make sure that our service is actually running. We should be able to, as a matter of fact, let's open an incognito window so we don't run into the problem of browser caching. Wonder if we can do HTTPS 92.168.100.50. Yep. Okay, so you can see that it works. It also works for .80, I believe. Excuse me, port 80. Notice I have it HTTP. Oops. Okay, so we get basically a web server running on port 80 and port 443, and they both are working. And that is coming from my IP address. So my IP address is 192.168.110.10. Let's go back to the diagram. So, okay, so it does. I don't have it labeled on here, but that's the address that I'm coming from. And sure enough, I get my web request answered. So then we're going to try it then from the 10.10.110.10. It's going to be a little bit more rudimentary here. We're going to use curl because this VM is very lightweight. Okay, so let's go. So the web server is actually here. You can see the IP address 10.10.120.10. And also on the inside of the network is 10.10.110.10. So that's a lot of tens, but nonetheless, we're going to give this a try. Curl. We'll just stick with HTTP. Okay, and we can see it's stalling, and eventually it'll fail. We're going to trigger it to fail because it shouldn't take that long. We'll take a look and see what's happening here in terms of packet captures. So I'm going to go to the ESXi host where the virtual machine lives, and just so you can follow along, let me go to my vCenter inventory. So web server 1, it's on ESXi host 1. Web server 2 is on ESXi host 2. So let's go to web server 2. So there's the VM and its port identifier for the DV switch. Packet capture on the switch port. Capture point. Oh, let me finish filling this out here. VNIC RX VNIC TX. I'm going to pipe that to TCP dump. Okay, that command's going to run, but before I finish that command, I should have done this, but it's on my lab. I already know what the ESXi host version is. Usually when you run this packet capture, you want to do VMware-L when you're on the command line of the host and figure out what the version is of your ESXi host. Reason being is that this syntax I'm using for the packet capture with capture VNIC RX and TX is packet capturing bidirectionally, and this feature actually was not possible in ESXi or vSphere generally 6.5 and below. So before 6.7 is the first version where you can do this. Previously, you had to do packet capture one direction at a time. So if you're wanting to do this and you go to packet capture bidirectionally and it doesn't work for you, then you might want to check the version. All right, but in any case, let's continue with the packet capture, and we're going to capture these flows here. Yeah, so let's send the traffic from the outside. We'll do port 80 traffic. Okay, that should have sent something. And sure enough, we see traffic coming across. Let's cancel the capture. So you can see source IP address does correspond with my IP address. And the destination does correspond with the destination 10.10.120.10. Despite the fact in my browser, you can see I clearly have sent it to 192.168.100.50. So destination NAT's working there. And that's no problem. That's basically just showing the packet captures of what we saw in the browser. Okay, so let's clear that. And packet capture again. And what happens when we send traffic from web 01A? Alright, so we have, it's an ARP. Here we go. Let's cancel. Alright, so here's the initial request, source from 10.10.110.10, destination 10.10.120.10 at port 80. Alright, and then you can see the web server is actually responding. Alright, but what's, it's weird. Why is that packet not getting back to the VM? Well, actually, let's take a look at that VM. So let's go to ESXi host 1. Okay, we have web 01A, and let's do a little shortcut here. Alright, we'll packet capture, and we will send the traffic again. We got our failure message, ESXi host, so we can see, we'll cancel this, that should be enough, so we can see the packets leaving from this VM, destined for 192.168.100.50, so that's what we expect, that's what we sent it to. But what you probably wouldn't expect is that the web server traffic is actually coming back to the VM. So this is actually the IP address of the web server. But notice what address it's sending it to. It's sending it to address 10.10.110.10, which makes sense, right? Because that's the address we're coming from. So it actually is doing what it's supposed to be doing. The problem is that the packet, my web server, or excuse me, my client sent a packet. We have some problems with the lab. It looks like my client sent a packet to 192.168.100.50. It didn't send a packet to 10.10.120.10. So when it receives this packet from port 80, it's going to drop the packet because it's saying I'm not expecting this. This isn't what I want. My web server, my client wants a packet from 192.168.100.50, and that's where TwiceNAT comes in. Okay, so we'll stick with the color that we have. So you'll notice from my VM, my client VM, the packet goes up to the Tier 0 gateway, goes down to the web server. The web server actually, it does go to the Tier 0 gateway. Keep in mind this is a virtual router, and the router interface is going to be living in the ESXi hypervisor, at least one of the interfaces. And it's going to be routed directly over here, because these two Tier 0 gateways share a connection to the distributed router of the Tier 0. And I don't want to go too deep into that. I'll just mention that the Tier 0 gateway, Tier 0 and Tier 1, but Tier 0 and Tier 1 can share this architecture, which is basically Tier 0 has an SR router and a DR. Okay, SR router stands for service router, DR stands for distributed router, and the distributed router is the component that combines all of these routers together. A portion of the Tier 0 gateway lives on the same ESXi hypervisor as the Tier 1 gateway on both of these tenants, so that the packet it does get routed through the Tier 1. It leaves the Tier 1 in the ESXi hypervisor, gets routed through the Tier 0, and then down to the other Tier 1. Again, this is all happening in the ESXi hypervisor. The reason why that's a problem is that your NAT rules happen here in the SR. And the SR VRF is actually not distributed. We can take a quick look at that. If I go to it's closed. Okay, so let me open. We're going to open the edge. Edge 01. All right. Okay, so we get logical router lists all the VRFs, all the VRFs on this edge, and you'll notice the one we're concerned about. I've been speaking about these. So these two constitute the Tier 0. The one I was just telling you about is the SR. That's the one we're concerned about. This is the one that does the NATing. This one, while present here, just note that it also lives in the ESXi hypervisor, co-located with this on this edge, but also a portion of it is located on the ESXi hypervisor where the Tier 1 gateways live. And if when the packet's taking the return traffic back to the client, it's not going to be, the NAT is not going to be reversed because this DR does not do NATing. So that is a little bit as to why it works that way. Right, a little bit different than traditional routing. So the way that we fix that is with the TwiceNAT, and I'll just go back to this diagram here. We need to set up a destination NAT. Well, a destination NAT happens first, and then a source NAT, we need to set that up as well. And one of the things that should be taken away from this diagram, when we configure the source NAT, it needs to have a definition of what destination NAT took place. So the destination NAT will occur, it will change the headers of the IP packet, and then the source NAT will need to occur based on that change that was previously made in the destination NAT. And the net result will be a TwiceNAT, and we will get traffic from one Tier 1 client, one tenant client to the other. So this will suddenly start working. So let's go ahead and build that rule. Add a NAT rule. Call it tenant to tenant source NAT. Source NAT. Okay, so we consider the destination NAT that's taking place. Right, it's changing it to 10.10.120.10. So that's what we want to have our destination IP address be in terms of defining what traffic are we looking to make a change on. So anything matching with the destination IP of 10.10.120.10/32. This time the source packet is going to be coming from our VM here, 10.10.110.10. And we're going to translate that to, so what we want to happen, undo all this. What we want to have happen is that when the packet comes from our client up to the tier 0 down through the tier 1, we want this packet to be returned back to the tier 0 SR so that the NAT can be reversed, and then our packet can be sent back to our client with a source IP address of 192.168.100.50. So let's continue that. Okay, we give the rule a couple seconds to initialize. All right. Okay, so source IP address is 10.10.110.10. Destination IP address is 10.10.120. Okay, so let's cut off there. 10.10.110.10. 10.10.120.10. And 192.168.100.50/32. So this looks like it will work. So let's try it. And sure enough, it works. So well, we'll do just one last piece. I mean, we can see that it's working. We'll take the packet capture again on host 1. And let's do a simultaneous packet capture on host 2 as well. We'll send it. Okay. So we'll look at host 2 first. You see the packet coming across. This time sourced from 192.168.100.50. Notice that's different than what we had before. Before it was 10.10. Wait. Wrong one. 10.10.110. We need to stop that. Okay. Okay, so before the packet was coming across with source IP address of 10.10.120.10. Okay. Now it's 192.168.100.50 as the source IP address. So the web server sends it back to that address, which goes to the service router. Then the service router sends it down to the web client, and everyone's happy. So this is something, again, I wanted to share because I've been wanting to know how to do this for, we'll say 2 years. Finally figured out how, and I wanted to share it. If I'm running into this issue, or I have clients running into this issue, certainly I'm not the only one, I would imagine. So hopefully this helps somebody as well. All right, bye.